Welcome to arc length of a polar curve. So the idea here is if we have a polar curve r equals f of theta on the interval from theta 1 to theta 2, we can view the polar curve as a parametric curve. Given by x equals f of theta cosine theta, or r cosine theta, and y equals f of theta sine theta, or r sine of theta, on the interval theta 1 to theta 2. And we know parametric curves how to find arc length. So we have the arc length is therefore equal to the definite integral from theta 1 to theta 2 of the square root of, we do dx d theta squared plus dy d theta squared, and then d theta. The only difference between this and our parametric arc length so far is that we're using theta in place of t. Otherwise, it's our standard formula for arc length of a parametric curve. So we also have, but we know that dx d theta is f prime of x times cosine theta minus f of x. Sorry, not x. These should be f prime of theta times cosine theta and f of theta. So we have dx d theta is equal to f prime of theta times cosine theta minus f of theta times sine of theta. And dy d theta is equal to f prime of theta times sine of theta plus f of theta times cosine theta. If we substitute these, expand out the power squares, and simplify, we wind up getting a very nice, pleasant formula. So if we expand out the squares, or if we substitute in and simplify, we get a very nice, simple formula. And the formula we wind up getting is for r equaling f of theta on the interval from theta 1 to theta 2. The arc length is equal to the definite interval from theta 1 to theta 2 of the square root of f of theta squared plus f prime of theta squared d theta. So the reasoning behind this, we'll get an f prime squared times cosine squared and an f prime squared times sine squared from squaring the dx d theta and dy d theta. Cosine squared plus sine squared is of course 1, gives us just that f prime squared. We will also get a f times sine squared and an f squared times sine squared and an f squared times cosine squared. Again, sine squared plus cosine squared is 1, gives us just that f squared term. And then the middle stuff cancels out since we have the minus in one case and the plus in the other. So we do wind up getting this fairly simple formula that does not require us to parameterize our polar equation first. So for example, let's go ahead and find the arc length of the rose curve r equals cosine of 2 theta. So this rose curve r equals cosine 2 theta winds up looking like a 4-petaled rose. And it turns out that it takes precisely 2 pi, from 0 to 2 pi. So once around the curve, corresponds to 0 is less than or equal to theta is less than or equal to 2 pi. And so these will be our endpoints of our curve. So we will consider 0 and 2 pi to be the endpoints of our curve. R equals cosine theta. This cosine, or sorry, R equals cosine 2 theta. This cosine 2 theta is our f of theta. So we have our endpoints of 0 and 2 pi. We have f of theta is cosine of 2 theta. F prime of theta would therefore be a negative 2 sine of 2 theta. And so we can go ahead and put together our formula. We get that the arc length is the definite integral from 0 to 2 pi of the square root of, we do f of theta squared. So cosine of 2 theta squared plus f prime of theta squared. So a negative 2 sine of 2 theta, both things squared, and then d theta. So we could rewrite this as the definite integral from 0 to 2 pi of the square root of cosine squared of 2 theta plus 4 times sine squared of 2 theta, and then d theta. I'm going to go ahead and just plug this into Desmos, and we will see what we get. So if we plug it into Desmos, we get about 9.688 as our arc length. So this curve is much more than a circle of radius 2, since we come in and out and in and out and in and out. With a circle of radius 2, we would expect to have sorry about that. I mean, this is more than a circle of radius 1, right? We were looking at cosine 2 theta, not 2 cosine theta. So this goes out as far as 1 for each petal. We expect it to have more sort of circumference than a circle of radius 1, since we come in and out quite a few times. And so we are larger than the 2 pi we would get if we went just around the edges. So it seems sort of to be a reasonable length. It's not yet equal to going around a circle twice, right? So again, this is how you can go about calculating arc length. It's in a lot of ways simpler than, or can be simpler than the parametric equation. even though that's where the formula comes from. So again, this is how we can go about finding arc length from a polar curve. You are welcome to plug into a Desmos or some other program to calculate that definite integral. At this point, I'm more concerned with your setup in the application problems.